In the presentation on power series, we took care of derivatives and integrals of power series, and on the algebraic side, we took care of sums and differences. We did not talk about products and quotients of power series, and the reason for that is that those can and do get a little messy. The underlying rule of thumb that power series act like infinite polynomials, that rule of thumb certainly stays in force. It's just that because the patterns might not be completely discernible anymore, the computations for products and quotients do get a little bit more complicated, and so the best thing that we can do here is to talk about how we can at least find the first couple of terms of a power series that is the product of two other power series or the quotient of two other power series. The underlying theorem is very similar to what you have seen for sums and differences, namely that products as well as quotients of power series are again power series, at least locally, because up to a certain radius those power series will still converge. Okay, let's take a look. If we wanted to, for example, take the function e to the z over z squared plus 1 and expand it into a power series around 0, well, we could try to work out Taylor polynomials, and we would realize very, very quickly that there is no good pattern that establishes itself in the derivatives. However, on the other hand, e to the z over z squared plus 1 is e to the z time for which we know a power series representation, and times 1 over 1 minus negative z squared. So that means that this is actually e to the z, which is the sum k equals 0 to infinity 1 over k factorial z to the k, times sum k equals 0 to infinity negative 1 to the k z to the 2k by just plugging negative z squared into the formula for the geometric series. Okay, so that is something that we can technically multiply out, but because it's an infinite sum, what we're going to do for the purposes of this class is that we just realize that the power series for the exponential function is 1 plus z squared over 2 factorial, which is 2, plus z cubed over 3 factorial, which is 6, plus z to the 4th over 4 factorial, which is 24, and so on. And we realize we can get as many terms as we need. Similarly, the power series here is 1 minus z squared plus z to the 4th minus z to the 6th, and so on. And again, here also we can get as many terms as needed. And, well, how do you multiply out polynomials? You multiply every term in the first parenthesis with every term in the second parenthesis, and then you collect terms. Well, every term here with every term here is infinitely many times infinitely many, which would take a while. But what we can see is that the powers increase, which means, for example, the z to the 4th times the z to the 6th will give a z to the 10th term. So if I'm only interested in terms up to power z to the 5th, for example, then I don't have to worry about terms of a certain order. And so then also in terms of sorting things, for the constant term, well, a term z squared, a term z cubed, and so on, as well as a term z squared, z to the 4th, and so on over here, that will not contribute to the constant term. So the constant term will just be 1 times 1, which is 1. If I'm now looking for the term with z, well, 1, if there was a z here, would contribute, but there is no z here. Z times 1 gives us a z, but then z times anything else gives us terms of order higher than z, so that's not going to do anything. And anything that has a z squared will also not contribute to the linear term, so we get 1 plus z. Now for the z squared term, we have to consider all the terms where the powers add up to 2. So I have 1 times, well, 1 times negative z squared, so that'll give us a negative z squared here. The z to the 4th will not contribute, and nothing further will contribute there. Z times 1 will not contribute to the z squared term. Z times z squared will not contribute to the z squared term, and the z times the higher order terms will also not contribute. But z squared over 2 times 1 is, of course, 1/2 times z squared, so we end up with z squared times negative 1 from the negative z squared times 1, plus 1/2 from the z squared over 2 from here. Then we're looking for the z cubed terms. Well, what do we get for z cubed? 1 times anything with an even power does not contribute to the z cubed. Z would have to be multiplied with z squared to give us a z cubed, and indeed that happens here, and we get a -1 because z times z squared is negative z cubed. The z squared times anything here doesn't give us a z cubed term. The z cubed over 6 times 1 gives us the plus 1/6. Z cubed times any of the higher order terms doesn't give us any further contributions to the z cubed. And z to the 4th and higher order terms here in the first parenthesis will not contribute to the z cubed. Let's do that one more time with the z to the 4th. So if I'm looking for the 4th order term, well, I have 1 times anything here only contributes to the z to the 4th term with the 1 times z to the 4th, which is the 1 here. The z times any even power term doesn't give us a z to the 4th, so that doesn't contribute. Z squared over 2 times 1 doesn't contribute, but z squared over 2 times negative z squared contributes, and that gives us negative z to the 4th over 2, which is the -1/2 here. Z cubed times even powers doesn't contribute to z to the 4th. Z to the 4th over 24 times 1 is z to the 4th over 24, which is the 1 over 24 here. Z to the 4th times the higher order terms in this parenthesis does not contribute anything further to the z to the 4th, and z to the 5th and higher order terms also do not contribute to this z to the 4th. We can see that this process can be continued as far out as we want to, and here I actually chose to just record the first 5 non-zero terms, and the rest now is simply algebra. The 1 stays a 1, the z stays a z. Z squared would be a -1/2 z squared here. Then we have -5/6 z cubed, and 1 minus 1/2 is 1/2, and 1/2 is 12 over 24, plus 1 over 24 is 13 over 24 z to the 4th. And again, if we need more terms, we can work these things out. So a typical problem in this realm would also specify how many terms people want to have, and that's how far out you're supposed to expand this with a product. Okay, for division, well, if I wanted to, for example, expand the function 1 over cosine z into a power series around 0, again, it'll be very challenging to do this with Taylor polynomials because there is no nicely discernible pattern. And so what we can do is, because the cosine of z is equal to its own Taylor series, which is 1 minus x squared over 2 plus x to the 4th over 24 minus x to the 6th over 720, and so on, we can obtain the first few terms of the expansion by simply generalizing the division of polynomials. So we will not get the full expansion, but that is okay, because the algorithm will show that the full expansion by straightforward division would really be a bit much to hope for, because there really is no pattern to discern. For the product, it is actually possible to write down a pattern, which is something you can see in books or maybe also in more advanced classes. I chose not to present that here. All right, so what I want to do is I want to take the function 1 and divide it by this infinite polynomial here, and we're only going to worry about the first 4 terms here. So let's see how far we can get here. Well, 1 times 1 will be 1, right? So now 1 times all this stuff has to be subtracted, just like in regular long division of polynomials. The only thing that is different here is that because we don't have a highest order term, rather than as in long division of polynomials going from highest order to lowest order, we actually work our way from lower order to higher order terms. So 1 times this stuff is the same thing, and we want to subtract, so we get 1 minus 1 is 0, and then 0 minus negative z squared over 2 is z squared over 2. 0 minus z to the 4th over 24 is negative z to the 4th over 24, and 0 minus negative z to the 6th over 720 is z to the 6th over 720. Okay, so how often does 1 go into z squared over 2? Well, z squared over 2 times. Z squared over 2 multiplied by all this gives us z squared over 2 times 1. z squared over 2 times negative z squared over 2 is negative z to the fourth over 4. Z squared over 2 times z to the fourth over 24 is z to the 6th over 48. Z squared over 2 times z to the 6th over 720 actually gives us z to the 8th, and we don't keep track of those anymore, so we stop right here. And if we subtract that out, we get z squared over 2 minus z squared over 2 goes away. Z to the fourth over 24 minus negative z to the fourth over 4. How does that go? That would be that z to the fourth over 4 is 6 over 24 z to the fourth minus 1 over 24 is 5 over 24 z to the fourth. And similarly here, the common denominator actually is, I think, 48 does go into 720 because 720 is 15 times 48. So we have 15 over 720 negative plus 1 over 720 is negative 14 over 720, and that gives us 7 over 360 after we simplify the fraction. How often does 1 go into 5z to the fourth over 24? Well, 5z to the fourth over 24 times. So we take 5z to the fourth over 24 times 1, which gives us the subtraction of 5z to the fourth over 24. 5z to the fourth over 24 times negative z squared over 2 is 5z to the 6th over 48, as we can see here. And so now we again would subtract. And how does that go? Well, the 5z to the fourth over 24 minus 5z to the fourth over 24, that goes away. Let's see if we can work out this fraction directly. Of course, we're going to get terms z to the 6th. 48, what was it? 15 times 48 was 720. Okay, 15 times 5 is 75. So we get plus 75 over 720 minus 14 over 720 is 61 over 720. And that's indeed what this is here, 61 over 720 times z to the 6th plus higher order terms. How often does 1 go into 61 z to the 6th over 720? Well, it goes into it 61 z to the 6th over 720 times. And if I subtract that out, I would get only higher order terms that we don't keep track of anymore, which means this polynomial is as well as we can do with this approach up to this order of accuracy. And then to double check whether this really is reasonable, we can certainly take a look at this polynomial and plot it and compare the plot to the plot of 1 over cosine z. And if we do that, with the polynomial being red and 1 over cosine x being blue, we see that the polynomial looks like this, like a 6th order polynomial with positive leading coefficient often does. And the function 1 over cosine x is very closely approximated by the polynomial near the point of expansion, which is how Taylor polynomials and Taylor series ought to work. And then, of course, because 1 over cosine x has a singularity at pi over 2 and at negative pi over 2, we cannot expect the polynomial to approximate, well, arbitrarily close to the singularity and certainly not beyond the singularity. So this one really is about as good as can be expected. The approximation can be improved, some by improving the order of the approximation, but that's left for further computations if you choose to do some. But overall, we can say, yeah, this does really work out very nicely. And that is the end of the example, and that is the end of this rather quick presentation, because, well, the principle really isn't that hard. The problem certainly lies in the details. I hope you don't have too many homework problems assigned for you to work out these multiplications and divisions, but either way, it's simply a matter of patience to get them done. Thank you.